In this video, we're going to look at the moment generating functions of two standard distributions, and then we're going to see an important theorem about moment generating functions. So the first standard distribution that we want to look at is a Poisson distribution. And a Poisson distribution, if x is Poisson, then it depends on, or it needs to have a parameter lambda specified. And this is information from your first probability course that you should remember about the Poisson distribution. The probability mass function is e to the minus lambda, lambda to the x over lambda over x factorial. The sum of the total probability equals 1. The expected value of a Poisson is lambda, and the variance of a Poisson is also lambda. So let's go ahead and calculate the moment generating function for a Poisson random variable. So we have the expected value of e to the tx. That's the definition of a moment generating function, as long as that is finite on some neighborhood including 0. So we have here, by using the LOTUS, by using the theorem for functions of random variables, we put e to the tx in front of the PMF, and we sum this over the entire support, x equals 0 to infinity. It's discrete, so we are summing, not integrating. Using a little law of exponents, we can bring the e to the t inside here, right? E to the tx is e to the t to the x, and then we can combine that with the lambda. So we have lambda times e to the t all to the x. Now this e to the minus lambda, as far as the sum is concerned, that's just a constant, because the sum is with respect to x, so I can bring that e to the minus lambda out. And then what we have here, what we have left, is something of this form. E to the z is, we saw this in a previous video, and you may remember it from your Cal 2, this is the Maclaurin series for e to the z, so e to the z is equal to the sum from n equals 0 to infinity of z to the n. And if we make the change here that my scripting variable is x instead of n, and the z is being replaced by e to the t lambda, then I can go ahead and tell this e to the z, right? So e to the t times lambda. Now, just using another law of exponents, right? Like bases, so we can add the exponents, and adding the exponents lets me factor out a lambda, and here is the moment generating function, e to the lambda times e to the t minus 1, and this function is finite on the entire real line, and so this is a valid moment generating function. We can use this to verify these results from your first probability course, and we can do that by taking the derivatives using our properties, that the nth derivative of the moment generating function evaluated at 0 gives us the expected value of x to the n. It gives us the nth moment about the origin. So if we take derivatives here using the chain rule, that is your derivative of the moment generating function, that is your first derivative. So the expected value is the first derivative of the moment generating function evaluated at 0, plugging t equals 0 everywhere, and you do in fact just get lambda. So that first result is verified. The second derivative, m double prime of t, needs a product rule. So I have to do, right, a sum of derivative of the first times the second. Well, derivative of the first as the same derivative that we had up here times the second, plus the first times the derivative of the second. Well, the derivative of the second stays the same. So there is your second derivative here. Now I can simplify that, but I'm not going to, because all I want to do is plug in t equals 0 anyway. So if I plug in 0 for everything here, I end up by getting lambda squared plus lambda. To verify the variance, I need to do the expected value of x squared minus the expected value of x all squared. So the expected value of x squared is here, lambda squared plus lambda, minus the expected value of x squared. So those lambda squareds are going to cancel out, and we get the variance is lambda, which is a result that you may have proven in your first course. If not, well, the moment generating functions makes the proof either accessible if it wasn't before, or probably even a little quicker. Let's look at our next example, and we're going to look at the standard normal. The standard normal random variable z is normal with parameters 0, 1. 0 we know is the mu, right? You would call this the mu of z is 0, and the standard deviation, the variance, the standard deviation squared, sigma squared, is 1. So the density function, which you might not have seen or you might not remember because we did not, or you did not use that much. You use the table for the CDF, but this is the density. This is the PDF of the normal. And when we did polar coordinates for the double integral, we figured out the double integral of this was, in fact, root 2 pi. So if we have 1 over root 2 pi, that makes this integral from minus infinity to infinity equal 1. That's the total probability. And then we just discussed the mu and the sigma, the mean and the variance here. We're going to calculate the moment generating function for that standard normal variable. So the expected value of t times z, no, e to the t times z, means that I put e to the t times z in front of the density function and I integrate on the support. The support is actually minus infinity to infinity. Now, we are going to be clever. It's always good to be clever if one can. And we are not actually going to integrate again because that was difficult using a double integral to evaluate a single integral here. But we are going to rely on this fact. We are going to come back to this fact in the integral. So let's take a look at what happens here. These exponentials have the same base and can be combined. They can be combined here. And we're going to pull this over into an aside and complete the square. If we go through minus 1/2 z squared plus tz and go through the steps, you should have no trouble seeing that this is the result when you complete the square for that quadratic in z. So if I plug that back up in here, another little law of exponents lets me split the exponent here and bring e to the 1/2 t squared out the front. What that leaves me with is the integral from minus infinity to infinity 1 over root 2 pi e to the minus 1/2 z minus t squared. Well, that's not quite what we had up here. There's this z, there's this minus t in the bracket. So how are we going to get rid of that? Well, a little u substitution will do the trick. If we let u equal z minus t, then du is dz. And taking care of the bounds, as z goes to infinity, u will go to infinity. And as z goes to minus infinity, u will go to minus infinity. So in terms of u, we have the same multiplier out in front, and now we have the integral from minus infinity to infinity of 1 over root 2 pi e to the minus 1/2 u squared du. Now that integral is exactly the same as that integral because the variable is a variable of convenience anyway. It is a dummy variable, so that is equal to 1. So we have e to the 1/2 t squared equals 1, or e to the 1/2 t squared. There is the moment generating function for a standard normal random variable that is valid on the entire real line, and so on an interval containing 0, and this is a valid moment generating function. So we know, right, we know that this is the mean and the variance here. Let's go through and just check real quick by taking derivatives here. So the first derivative of the moment generating function gives me this. evaluating at 0, I get e to the 0 equals 1 times 0, so that gives me 0. The second derivative is this. This is e to the z squared. Evaluated at 0, you get 1. And of course, the last thing that we want for the variance of z is e to the z squared minus e to the z all squared, and so we get 1 squared, no, 1 minus 0, 1 minus 0 squared, which gives me 1. And so the mean and the variance do pop out to be the same, as well they should, from the moment generating function. So why look at standard distributions? Why does it matter? This theorem is going to be very important for when we start talking next lesson about more than one random variable at the same time. So let's let m sub x of t and m sub y of t be moment generating functions for two different random variables for x and y respectively. Then this is a very powerful result, and its proof is actually quite difficult. So we will not even attempt to do so here, but this is a powerful theorem. If the moment generating functions are equal for all values of t, then x and y have the same probability distribution. So what that means, if something pops up that has this moment this moment generating function, then we know it can only be a standard normal random variable. The same thing back up here with the Poisson. If we find that we have a moment generating function which looks like this, there is only one distribution that has that moment generating function, and that is the Poisson distribution. So it's going to help us, this theorem is going to help us identify distributions when we start adding adding variables, random variables together.